Good morning, I am Paul Ceralde, and today we'll talk about Plasmonic Topological Insulators with nanocone structures, a project spearheaded by researchers from Royal Melbourne Institute of Technology. Topological insulators are materials having metallic surfaces and dielectric cores. They are vital for manipulation of optical properties and are likened to nanoscopic composites. For this study, a topological insulator in the form of crystals made up of bismuth, antimony, tellurium, and selenium was used. Plasmonic metals possess superb optical properties rooted from the material's electronic bond structure. Naturally, a metallic bond structure has overlapping valence and conduction bonds, meaning free electrons easily transfer when excited, therefore making them electrically conductive. However, for metals such as silver and gold, significant amount of the electrons are trapped in between the transition bands, resulting to bound electrons. These electrons behave in a group dynamics, which in more technical term is called the plasma. In addition, they behave like harmonic oscillators, as each interact with fixed positive ions in the surrounding. Note that we use the word plasmon as the quantum of these oscillations, as phonons are used for bulk vibrations. Now we have the Drude model of electrical conduction, showing how bound electrons affect the material's dielectric function by attributing it to the imaginary part of the graph. Below is a graph of the dielectric function of gold. The blue lines represent the real dielectric values, while the broken lines show the imaginary part, associated to bound electrons. In between a plasmonic metal and a dielectric material, the plasma oscillates naturally because of the opposite polarities existing in between the different interfaces. The negative value of the dielectric constant may be attributed to the imaginary contribution of the bound electron. Due to attenuation, the oscillation only exists at shallow skin depths of the material, as the vertical component decays through the material. It makes the event superficial and in a way confines the wave near surfaces. For optical applications, light is allowed to couple with surface plasmons by allowing it to be incident on prisms or dielectric crystals. That way, the incident light is polarized, resulting to a frequency that can achieve resonance with the surface plasmon for certain values. This phenomenon leads to a self-sustaining, propagating electromagnetic wave known as a surface plasmon polariton, which generate intense localized optical fields resulting to astounding optical properties, such as ultra-high index of refraction for the bulk of the material, and negative indices at the surface. Notice how this index of refractions exists within visible range. It is very sensitive to wide range of spectrum, and also provides superb light absorption and backscattering capabilities for light manipulation. The BSDS crystals used in the study display such property intrinsically. The material possesses a core-shell topological insulator structure that conducts photon-plasmon interaction, resulting to plasmon polaritons. The crystals were nanofabricated using focused ion beam system, which uses the same principle as the scanning electron microscopes, but with finely focused high-energy ions instead of electrons. Essentially, a high-energy gallium ion beam having positive charge hits the material surface to display a certain level of the material's molecules. This method is commonly used for nano-etching as shown on the left. The conical patterns was administered using two cross grating with variant periods to manipulate the topography. As shown on the distribution contour, the conical structure enhances the surface plasmon polariton resonance at the surface, as represented by localized high-intensity EM wave. The conical structure also resulted to anisotropy of the material, meaning it is equally absorptive and sensitive to light regardless of direction. The graph below also shows improved solar energy absorption as compared to typical silicon-based crystals. Such methods have already been used by a few patents submitted in the US. However, the use of topological insulators and nanocone structures for optical applications were done separately. The result of this study is a breakthrough for optical technology advancement and biotechnology alike. This type of surface may improve Raman scattering used in bioassays as it brings broader spectrum sensitivity and larger scattering angles for stain detections. This stable plasmonic metamaterial is also key in revolutionizing the shift of devices from electronic to photonic materials. A narrow channel surface can also be used as a transformative guide that traps and compresses the wavelength of incoming light to a fraction of its original value. This paves the way to development of nanocircuits and lab-on-a-chip technology.